Can you guys hear me in back? Sort of. Is this better? All right. So today I'm here to talk to you guys about the possibility for eliminating packet loss during BGP convergence. My name is Nate Cushman, as Todd said, and this is joint work with some colleagues of mine at MIT and CMU. So the problem that we're looking at is that BGP convergence causes you guys packet loss. You guys know this already, but let me go over a few of the measurement studies that have talked about this. A few years ago, Craig Labovitz came up here and told you that route changes can cause up to 30% packet loss for more than 2 minutes. A more recent study, including Randy Bush, has found that even for domains which are dual home to Tier 1 providers, a failover event can cause multiple loss bursts, and one of these loss bursts can last for up to 20 seconds. In a related study, they found that both popular and unpopular prefixes experienced loss during BGP convergence. And finally, we did a study of our own, looking at cross-domain VoIP calls. And what we found is that 50% of the disruptions seen in these type of VoIP calls were very highly correlated with BGP updates. But today I'm here to talk to you about the solution to this problem. So what kind of solution do we really want? We would really like a solution which eliminates packet loss during BGP convergence. But even more than that, proposals which have looked at BGP have generally run into the problem that until a majority of ASs deploy them, no individual AS sees significant benefit. So instead, we'd like a solution where an adopting ISP can protect itself and its customers from loss, even if no other ISP cooperates. So let's look at a little more detail about what causes packet loss during BGP convergence. To do this, let's imagine a hypothetical example where Avi's decided to start his own ISP again. And being the internet superpower that he is, he was able to negotiate peering relationships with some of the Tier 1s. Patrick also decided to start an ISP, but he didn't fare as well. And he was forced to buy service from Avi and AT&T. Now, initially, Avi and AT&T are both routing through Patrick to get to MIT. And since all of Patrick's providers are using him to get to MIT, he has no alternative path to the destination. Thus, when the link goes down, Patrick knows no alternative path to the destination and is forced to immediately start dropping packets. This makes Patrick very sad. Even worse than this, however, Patrick's not just dropping his own packets. He's dropping packets from both AT&T and Avi as well. And that makes Avi very angry. Eventually, of course, Patrick's going to send out a withdrawal. AT&T and Avi are going to stop routing through him. AT&T will advertise the path through Sprint, and routing will happen normally again. In the meantime, however, Avi, AT&T, and Patrick all saw significant packet loss. And this isn't just an isolated incident. Remember, the measurement studies show us that significant loss happens in today's internet, even when ISPs are connected to Tier 1s. So how do we solve Patrick's problem?
This one.
Yeah. we want to tell Patrick a failover path before the link fails, rather than afterwards, as is often the case in current BGP. So let's see how this would work in our example. AT&T might advertise as a failover path to Patrick the AT&T Sprint MIT path. And this advertisement is done before the link fails. Thus, when the link fails, Patrick can immediately start routing along this failover path, thus completely avoiding packet loss. Now note that the rest of BGP convergence happens just as it did before. The only difference is that Patrick is able to route along this failover path in the meantime. So how does this actually work in practice? How do we make this work? Really, we need only two simple rules in order to make this work. The first is, when do we advertise these failover paths? And all we need is for each router to advertise only one failover path and only to the next hop router on its primary path. Now note that normally routers advertise no path to the next hop. And the reason for this is because if you're routing through someone, you don't advertise him a path. And in order for the forwarding on the failover paths to work, some router immediately above the downlink is going to start traffic on the failover path. In order to ensure that it continues along the failover path, when a router receives a packet from the next hop interface for their primary path, they forward the packet along the failover path. And with these two simple rules, we can guarantee that a router will see no BGP-caused packet loss during convergence, as long as it will have what we call a valley-free path to the destination at convergence. And a valley-free path is purely a path where no AS along the path is doing transit for a non-customer. No one's routing from a peer to a peer or from a provider to another provider. So surprisingly, this helps us not just in the interdomain scenario, though. It actually helps us even when deployed just in a single AS. To understand how that's possible, let's take another example. So let's imagine that Patrick's actually able to negotiate a peering relationship. And let's imagine that he negotiates that with an AS named Joe, who has a direct path to MIT. Now you might think, okay, well if that's the case, then Patrick's going to already know an alternate path and we don't need any of this failover path business. But actually, that's not correct. And the reason for that is, well, yes, router 1 will know an alternate path when the link fails. He's not going to advertise that path to router 2 because router 1 is routing through router 2. And as a result, when the link goes down, router 2 will still be left without a path, causing him to immediately start dropping packets. Instead, with failover paths, router 1 will offer a failover path through Joe to router 2 before the link goes down. Thus, when the link goes down, router 2 U-turns back to router 1. Router 1 recognizes that these packets are coming on the interface, on its primary path interface, and as a result forwards them on the failover path back towards Joe, thus completely avoiding loss. So let's see how this works in practice. Because we want to see how this works at the internet scale, we need to do this in simulation. So what we've done is we've run a router-level simulation across the full internet. To do that, we build AS graphs based on both route views and write BGP data. Then we use inference algorithms similar to the ones that Renesas uses for their tools to annotate links with customer, provider, and peering relationships. And then we add border routers on these connections. We add border routers in each of the ASs based on the connections to other ASs. And for our simulation, we use the RFC-based internal MRI of 5 seconds and the external MRI of 30 seconds. For each experiment, we pick a random destination, we take down a random link on the network, and we find the duration of packet loss for routers which were using that link before the link went down, but still had a path to the destination after the link went down. And we run this for 1,000 randomly chosen links and destinations for each experiment. So first we said that one of our goals is to ensure that just deploying this in a single AS provides significant benefit. So let's focus on AT&T. Looking just at packet loss when running BGP, this graph shows us on the left side here, we see the fraction of routers which were using the link before it went down. And on the x-axis here, we see the duration of packet loss seen by these routers. And I want you to focus on one point here, this point here. What this point shows is that approximately 20% of routers see more than 30 seconds of packet loss. Now, you might be thinking, okay, well, if I'm AT&T and I just want to make a change within my own AS in order to improve BGP, why don't I just reduce the MRAI? Well, so what we did is we looked at reducing both the internal and the external MRAI all the way down to 0, which we think would be the best possible scenario from that perspective. And what we find is, in fact, that helps us relatively little. We still see significant packet loss in this case. And even worse, what this does is it doubles the number of updates, not just for AT&T, but for all of its customers as well, providing a significant burden to all of its customers. Now let's look at what happens if we deploy just our failover path based mechanism just inside AT&T. We see significant reduction in the packet loss. In fact, we see less than 3% of routers see more than 30 seconds of packet loss when just AT&T deploys the failover-based mechanism. Now, how is it possible that deploying this just inside AT&T had such a significant effect on the packet loss? And the reason for that comes back to a simple fact about BGP, which is that the bad news, the withdrawals travel very quickly, whereas the good news, the advertisements, follow only on very slowly. And thus what happens is even a single border router in AT&T loses connectivity for a moment. It sends out a withdrawal, which quickly travels out to all of its customers. But the advertisement, which may follow, is going to often get stuck behind an MRAI. And as a result of that, those customers, in the meantime, are left without any path to the destination. Thus, by providing failover paths, even just internal to a single AS, we're able to almost completely avoid those type of spurious withdrawals and the ensuing packet loss that they cause. So we also said that we want to ensure that this completely eliminates packet loss network-wide if we deploy it in all ASs. So we ran another experiment where we looked not just at loss for AT&T and its customers, but for the entire network. And we see two things from this graph. The first is we see that the loss for BGP is very similar to that with running just in AT&T. And that's because AT&T's customers don't actually look all that different from the average router on the internet. And as a result, most of the internet sees a loss similar to that of AT&T's customers. The second thing we see, and more importantly though, is that deploying this everywhere gives us completely connected all the time, completely eliminates packet loss. So you might be thinking, okay, fine, so we've eliminated packet loss, but at what cost? Maintaining these failover paths must be increasing the number of updates. And in fact, we find a relatively small increase in the number of updates is necessary. And the reason for this is that all we're doing in most part is replacing what would have been a withdrawal message with the advertisement of a failover path instead. And so in fact, we see less than 5% increase in the number of updates necessary. So to conclude, I'd like to summarize what I've told you today. I've told you about a simple mechanism, which is to offer a failover path only to my next top neighbor. This mechanism solves the problem that we initially posed, which is that we eliminate packet loss resulting from BGP convergence. And this solution is relatively deployable. And by deployable, I mean that an adopting ISP can reduce loss even if no other ISP cooperates. And for those of you that are interested in this topic, I encourage you to come talk to me afterwards or send me email. I don't have any detailed documents online yet, but I'm in the process of writing a couple of papers on this, both of which will come up shortly. And now I'll take questions. Thanks a lot.
Excellent. Thank you. Are there any questions? Questions? Yeah, you can't just raise your hand. You have to go to the mic. This is not third grade. And can I get the first lightning talk speaker, Chris Street, up here as well, please?
This is Dana Blair with Cisco. Does the backup path, or whatever you call it, assume a separate circuit?
Separate? You mean a separate link?
Physical circuit.
No, the failover path is a virtual path essentially that uses exactly the same links as the normal path.
So if it used the same circuit and you reroute the packets, turn them around, how does the upstream router know to route them back?
So the upstream router knows to not route them back based on the forwarding rule that I told you, which is that if the primary path that I would send this router along is the interface that I just received this packet from, then I know that it's destined for the failover path. And as a result, I forward it on the failover path instead.
Okay.
So as long as I have the information of which interface this packet came with when I do the lookup, I can tell.
Good. And we're doing these three people lined up fast, and then we're done. Yes, sir.
I just had a question, Marshall Eubanks here. I just had a question about loop detection. I mean, is this guaranteed to be loop free?
Yeah, so that's a very good point, actually. I only had 15 minutes, so I didn't talk about the loop avoidance mechanism, but we have an additional mechanism where we annotate a little bit of information in the BGP update itself in order to ensure that we can avoid loops as well during convergence.
Yes, sir.
Yes, Eric Carroll. I'd like to understand how you see the difference between your solution versus a link state routing algorithm where the node is at the AS level. Have you thought about the differences between that?
So, I mean, that's a very good question, and there's a couple of answers to that. The first is that the problem with link state at the AS level is that you end up getting a lot of updates for information that you don't care about at all, for paths that you aren't, for links that you aren't using for any of your routing. And the other part, sorry, okay. And in fact, even with link state running network wide, that doesn't guarantee that you're not going to see packet loss, because the link state still needs to, the link state information still needs to reach all the way across the network, which, you know, as the internet grows, it's going to take longer and longer for that information to propagate. And especially if we're sending a lot of updates, which means that routers need to spend a lot of time processing this information, which even slows it down further. The idea here is that the router immediately above the downlink, it already knows a failover path, which it can immediately use. And then we allow convergence to happen normally, but in the meantime, we're sending packets along this failover path and not dropping them.
So you're basically saying that this is a localized link state to that specific edge between the two ASs.
I guess you're right in that sense, in the sense that the router is aware of the state of the link directly connected to it. But what we're not doing is sending this link state information between routers, though.
Okay, thank you for an interesting presentation.
Okay, thanks.
Yes, sir.
Michael Richardson, very good presentation. I assume that the failover path is per prefix?
The failover path is per prefix.
Okay,
That's
thank
correct.
Danny McPherson. So yeah, on the per prefix thing, that was actually one of my observations. And I'd say that, you know, so you talked about loop detection on the control plane, and I would be more concerned with forwarding loop detection, which is going to be the big issue. And then two other comments. One was the MRAI with hierarchy inside of a network, the number of paths and the number of updates and the replication and those things is a much bigger issue. And the final thing I had was I'd recommend that you actually attend the fib limits BOF this afternoon and have a look at that, because all this stuff has to happen in the forwarding path, and adding, you know, doubling the size of that, you know, arbitrarily or even more than that would be a very big issue, much less some small incremental update. So.
Yeah, and that's actually a good point in itself, in that there's a couple of answers to the last forwarding point one, which is that it depends on the router architecture a lot, of course, but these things don't necessarily have to be in the forwarding table before the link goes down. They could potentially be loaded on demand. Obviously, there's additional delay that's caused by that, but since these routers can recognize that these packets are coming from, they can recognize that they're in a state where they need to use the use the failover path, they can actually load these entries into the forwarding table on demand.
I don't think you want a control plane data-driven function to, you know,
Yeah, there are some issues with that, and in fact, we discussed that. We're working on exactly those kinds of issues in the papers.
And one other thing is there's been a huge amount of discussion in the IETF on the routing area working group mailing list about fast reroute for IGPs and dealing with just this problem. And I'd recommend that you have a look at some of that as well. But
yeah, in
thank
fact,
you.
I have been watching some of that pretty carefully.
Okay.
So thanks a lot, man.
Excellent. Thanks very much.